Hello and welcome to this course on MATLAB programming for numerical computations. We are in week 12 of this course. In this week, we are covering overall what we have done in the last 11 weeks, as well as talking about some of the ways in which the numerical methods can be used effectively to solve complex problems. I'm also trying to touch base upon some of the practical issues and so on, something that I have covered in the past in various weeks, but just kind of trying to recap them so that we finish off this particular course with a few interesting examples. In today's lecture, I'm going to talk about how to do regression and numerical differentiation with real world data. Okay, so now this data is modified data from some of the work that we have done in the lab. It's simulation based work that we have done in the lab. What we are trying to correlate is basically some parameter R with temperature. So the temperature is varied in a large range. It's a normalized temperature between 0 and 2.5. Okay, and with the change in the temperature or with the change in normalized temperature, we have the R that is changing. Okay, when we actually got the experimental data and try to build a model along with it, we realized that the model has a particular form. It follows some kind of a superlinear behavior. What I mean by that is, as the temperature increased, the overall R value reduced. It did not reduce linearly, it reduced with reduced as t by t naught to the power 1.3 or something like that. Okay, so based on that particular set of data and that experience, what I did is I thought, okay, let me make a numerical problem that I can solve in a lecture like this. So this is not an actual real world data, but this is a mock real world data which is based on our experience in the lab. Okay, so the red lines, the red dots over here actually show the data that was collected in the experiments, and the blue line over here shows that what data might have been if this was a perfect system. Okay, note that when you actually collect the data from the experiment, data is never perfect. For example, typical experimental errors can be anywhere between 2 to 10% for engineering experiments. So let me run this. Okay, so and let me plot the plot that you had already seen earlier. Let me plot t. And this is the plot that you get. So this is the experimental data, and this is the ideal data if there were no measurement problems in the experiment. Okay, that's how this looks like. Let's see and let's find out what the errors are. Okay, so if we were to get okay, so these are the errors that you will get. So the first data has 1% error, 4% error, 5% error, 9.5%, 9.6% and 4.5% error. Okay, so the small amount of error, that error is associated with experimental error. Okay, now let's say that our aim was to find numerical derivatives. Okay, now if we were to do numerical derivatives with noisy data, we are going to get large amount of errors. This is not very noisy data, this is moderately noisy data. So let's actually, what we will do is we will find the numerical derivative between the red data which is experimentally obtained data, and compare it with numerical derivatives obtained using the blue data. Okay. So, let us do it at at a few points. Let us do it at, for example, this point, and let us do it maybe at this point, right. So, this is so this is what we will get. Okay. So, let us calculate the numerical derivative. This is the numerical derivative, right. So, this numerical derivative calculated from the measured data is minus 0.36. The numerical derivative calculated from clean data is minus 0.2680. So, the error is minus. Okay, we get as high as 34% error. Okay, although the error in the original data was just around 10% or less than 10%, the error in calculation of the numerical derivative is as high as 30%. Okay, so let us calculate the numerical derivatives, okay, at various locations. So, let us say for I equal to 2 to 5, right. So, there are 6 data points. So, we will be able to use central difference formula for 2, 3, 4, 5. Oops. Okay. Okay. And let us display at those various points the two derivatives. Okay. So, let us run this. Okay. So, as you can see, the two derivatives do differ. In this particular data point, the two derivatives are differing quite significantly. Over here, the difference between the two derivatives is not very high. That here, the two derivatives are reasonably far apart. But in this particular data point, Okay, it so happens that the derivatives were significantly apart. As you saw earlier, as much as 30% error was observed in those derivatives. Okay, now why does this happen? Okay, so if you look at this data point and this data point, okay, this data point happens to have the error in the negative direction, this happens to have error in the positive direction. As a result of that, okay, the difference, when you take the difference between the two, it goes away from the actual derivative by a significant amount. On the other hand, if we were to calculate the numerical derivative at this point, okay, both this data as well as this data, okay, have errors in the negative direction. So errors in this particular case have a way of cancelling themselves out. Okay, that's why we don't see as much error when we calculated the numerical derivative at 1.5, but when we calculated the numerical derivative at 1.0, we saw a fairly large error. Okay, so as you can see, at 1.5 we did not see significant error between the two. Okay, so what's the solution? What's the way out for this? Okay, so the standard approach for handling this type of problem is, one approach is to do filtering. Okay, we are not going to cover that. You can look up any of your advanced signal processing texts in order to know how you can do the filtering, and then you can work with the filtered data. Alternatively, what we can do is we can try to fit a polynomial curve. Okay, let's say we are going to fit a curve of the nature okay. In that case, our dy by dt by t naught is going to be nothing but okay, that's what this is going to be. Okay, so let's first fit a curve of this nature. Okay, and if you recall from week number 6, how do you fit a curve of that nature? We will define capital Y as for I equal to 2 to 5. Okay, so what we have done over here is we have tried to do the regression and fit a curve. Okay, and after that we are actually trying to find out how the numerically computed algebraically computed derivative for the fitted curve looks like. Okay, how do you calculate the algebraic derivative? Is a plus 2a1 plus 2a2 into t. Okay, a1 plus 2a2 into t, okay, at the ith location. Okay, so that is how we are going to calculate this. So let's go over here and run this and see what we get. Okay, so these are the derivatives, and we can compare. So as you see, for most of the data points, okay, this regression based fitting has resulted in numerical derivative that's closer to the ideal value. Okay, so let me actually do this so that we can see the difference very clearly. Okay, so as you can see, the overall difference between the numerically calculated derivative and the actual derivative, if there was no noise in the data, has been decreased for most of the data points. Again, sometimes, not always, you will have that decrease. Sometimes you will see cases where you get a higher amount of error. Okay, so that was basically what I wanted to demonstrate. Okay, the primary point of this particular lecture was that the things that I have tried to cover in this particular 11 weeks plus this 12th week are things that are of practical significance. Okay, sometimes there are no correct answers, especially when dealing with experimental data, when dealing with research data. You have multiple options. What you want to do is you can try out those multiple options and compare them with what is known to be the truth. Okay, for example, we tried out two options over here. One is the direct numerical derivative and the second one was regression based numerical derivative. Okay, and both of them we compared it with, in this particular case, it was what was available for me was the truth. Okay, so we tried to compare it with the truth, tried to compare it with known data. Okay, and we found that one of the method works better than the other method. Okay, lot of times, especially in research or in industry, you will face with these multiple options, you will face with multiple choices, and you will need to make a judicious decision. That judicious decision is being made by comparing the various alternative and going with the alternative that seems most appropriate for the data and for the condition that you have. Okay, what I'm trying to explain over here is that the concepts that we have covered in the initial part of this particular course are the primary concepts that are going to go with you or stay with you for your future careers as scientists or engineers. Okay, that's the primary take home message that I want to give you in this second last lecture of this course. Okay, so I hope this video was enjoyable for you. Thanks for watching and see you in the next video. Bye.